Let's explore Go's unsafe package. This package enables low-level memory access and performance optimization. However, use it with extreme caution. The unsafe package is a built-in Go package that bypasses Go's type safety and memory safety guarantees. It allows for direct memory manipulation, pointer arithmetic operations, and circumvention of the type system. Core capabilities include converting between pointer types, getting memory addresses, calculating pointer offsets, and accessing raw memory. The unsafe package revolves around two primary types, unsafe.Pointer and uintptr. An unsafe pointer is a generic pointer type that can point to any variable. For example, you can declare a variable ptr of type unsafe.Pointer and assign it the address of a variable x. Then there is uintptr, which is an integer type that can hold memory addresses, facilitating arithmetic operations on those addresses. You can convert an unsafe pointer to a uintptr and vice versa, enabling pointer arithmetic. The unsafe package provides a couple of core functions. The size of function returns the size in bytes of the variable, as shown in this example. Then there is the offset of function, which returns the offset of a struct field from the start of the struct. Understanding these functions is very crucial when working with unsafe operations. Here is an example of type conversion using unsafe package. The unsafe.Pointer acts as a bridge between different pointer types. It allows reinterpreting memory as different data types. However, keep in mind that there are no type checking or safety guarantees when using this method. Here is a pointer arithmetic example. You can convert a pointer to umin parameter for arithmetic operations. Add element size to navigate array elements. Convert back to typed pointer to access value. So, in the given example, we have declared an array of 5 integers. We are trying to access the second element by incrementing the pointer. The unsafe package offers certain performance benefits like zero-copy operations, avoiding type conversions, direct memory access, and reduced allocations. This makes it valuable in specific use cases like system programming, high-performance libraries, memory-mapped files, and C interoperability. When working with the unsafe package, adhere to these safety rules. Always validate pointer bounds. Keep unsafe operations minimal. Document unsafe code thoroughly. Test extensively with the race detector. Avoid unsafe operations in public APIs. Remember that unsafe code breaks Go's memory safety guarantees and can lead to crashes, data corruption, and security vulnerabilities.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.